So here we're looking at 2.6 pulleys. So in all AS questions, the pulley system will be smooth. There's a picture in the top right hand corner of a pulley if you are unsure of what we mean by a pulley system. We do have a couple of modelling things that we need to learn. So when we're given light in an extensible, the acceleration of both particles has the same magnitude but acts in opposite directions. The smooth pulley, we're using that the tension is the same on both sides of the pulley. So the modelling situations that we've got here are very, very similar to what we saw on the last section. It's about acceleration being the same and tension being the same. So let's have a look at example 2.6.1. So we have a pulley system here. The first thing to do is consider all the forces that are acting on each of the particles. So I'm going to start with particle A. Because we have a smooth pulley, we know that the tension is the same on either side. So I've got tension acting upwards, and I'll explain why that is upwards in a second. For we're doing part A, so the mass of particle A is 2 kilograms, so its weight is 2g, and that will be acting downwards. And for B, it is 5 kilograms, and it has a weight of 5g. Because the string is light and inextensible, that means that the acceleration is the same on both sides, and because 5 is bigger than 2, it's going to have to move that way. So that's just a little bit of common sense in which direction it is going to move. And that's it. So that's how you put the forces onto the pulley system. And the good thing about these questions is that when you've got the vertical pulley system is it's always going to be the same. So you can learn this one. Just going to briefly talk about the forces acting on the pulley, which explains why the tension is acting upwards. So there are two forces that are acting on the pulley, and this is the one that we refer to in the modelling situation really. Because the pulley is smooth, that's not going to affect the tension either side, and it is equal and opposite to the red tensions. So just have a think about it. If you add two weights to a piece of string, then those weights are going to be pulling downwards, and therefore you get those two forces, the tension in the string that is pulling down on the pulley. Okay. Then we've got equal and opposite, so that's Newton's third law of motion in terms of those two tensions. If you're unsure on which direction the tension needs to be going in, just a little bit of common sense. If you'd have drawn the red tension going downwards, if you just think about particle A, something has to pull it up. So the weight is always going to be acting downwards. If the tension in the string is also acting downwards on particle A, then there is nothing to pull it up, and it will just move in the direction of both of its forces because the resultant force will be downwards. So that's how we draw the system. You've actually got three sets of forces: the forces on A, the forces on B, and the forces on the pulley. For this question, I am not interested in the forces on the pulley, but later on we will see a question where we're asked about it. So if we have a look at part A, and I'm going to do parts 1 and 2 together. So you can do these two together. You can do this as a system, so a whole system, just using F equals ma as one system, but just so that we keep it in keeping with what we've looked at previously, I'm going to do it as two separate F equals ma. So using Newton's second law of motion, I'm going to look at F equals ma on particle A. It is moving upwards, so that means we've got T, take away 2g, is equal to mass times acceleration, and then for particle B, which is moving downwards, so its leading force is 5g, and then the one against motion is tension, so that's take away, is equal to 5a, mass times acceleration. Now it's the same as what we've seen previously. So equation 1, equation 2, simultaneous equations, I'm going to add them to eliminate the tension. So because they're opposite signs, I need to add them. Just be careful here. So it's 5g take away 2g is equal to 5a add 2a. As is the case with these systems, because the mass and the weight is the same, you end up with one side being 5 take away 2 and the other side being 5 add 2, and there are slip-ups made there quite often. So do be careful with that. So we get A is equal to 3g over 7. It's important, especially on these questions that have multiple parts, to write down the exact value and then to give your answer to two significant figures. So I would encourage you to do both. Once we've done that, then we can work out what the tension is, and I'm going to consider substituting it into equation 1 because the tension is positive there. So I've got 2 times, I'm going to go for the full value, and then I add 2g. And when I do that, two significant figures, I get my tension to be 28 newtons. If you wanted to do this system in one go, then your equation of motion, so your F equals ma, would be this line of working here. So you've got 5g, take away tension, add tension, take away 2g, but I wouldn't encourage that unless you are familiar with using F equals ma and you're happy. And again, I would encourage you to write it down. If you're writing your equations for F equals ma for A and B separately, then you can skip this line of working here and go straight to the 3g equals 7a, because you should be able to add those equations together. But if you're not writing them down and you're going to go for it in one just to find the acceleration, then I would encourage you to show all your forces, because that's where all the marks are going to come from. So moving on, find the time for mass B to reach the ground. So it's starting up here and it's reaching the ground, and we know from the question that we're working on that D is equal to 0.9 metres. As soon as I get this information, I should be thinking SUVAT equation. So for part 3, I'm going to go with the SUVAT because it is asking about time and distance. As soon as it's speed, time or distance, you go straight into SUVAT. So we know that the distance or the displacement is 0.9. We were told in the question that we were released from rest, so that's that starting point there. The acceleration, again, full value, 3g over 7, and the time is what I'm looking for. Now, because I'm starting up here and finishing down here, my motion is in the same direction as my acceleration, and therefore both of those are taking the same sign, so I don't need to worry about the signs here because I've not got two directions like we sometimes do in the vertical motion questions. So the SUVAT equations which are given in the formula book, write down your equation, substitute in your known values, and then at that point pick up your calculator and we end up with, so we've got 0.9 is equal to 2.1 t squared, t is equal to 0.65 seconds to two significant figures. So looking at part B, what you want to do now is pause the video and have a go at part B, and then you can just flick through the video and check your answer as you go. So we've got acceleration pointing in that direction, and there's your forces. So B is still 5g in weight, A is 4g in weight, and because 5 is bigger than 4, it will be going, B will be moving downwards. For A, F equals ma is t minus 4g equals 4a, because it's moving upwards, so t is the stronger force. And for B, F equals ma, 5g is the stronger force. Simultaneous equations by adding, so I've done 5g minus 4g, and then for A, add 5a, the t has been eliminated. Then we've got A is equal to 9 over g, which is 1.1 metres per second squared, to two significant figures. Substitute into either equation. One is easier because t is positive, and you will get the answer of 44 newtons for tension. For part 3, mentioned time, we're doing SUVATs. S is 1, u, because it's at rest, is 0, the acceleration is 9 over g, and time is what we're looking for, and that leads us to 1.4 seconds. Let's have a look at example 2.6.2. So it's the same sort of system. Particles P and Q have masses 2m and 3m. Now when you get given a question like this, where we're given the masses in terms of algebra, then that doesn't mean that you can just come up with a value for what you think that algebra should be. So just because it's got 2m and 3m in there, I'm still going to be working with those values. So if we put the forces on, that's 2 mg. I just work with it in exactly the same way. That's 3 mg. And we've got tension the string passes over a smooth pulley, that's why my tension is equal, and the masses hang with the string taut. The system is released from rest. That might be useful later. Because 3 is bigger than 2 and we haven't been given any other information in the question, we are moving in that direction. We've got a light and extensible string. Okay. Find the acceleration of each mass. So, setting up particle P, F equals ma, we have got T minus 2 mg is equal to 2 ma, and for Q we have got 3 mg minus T is equal to 3 ma. Adding those two equations together, so just with practice you can see that this is getting a bit repetitive. Therefore these questions, these are the ones you hope come up, because it should be obvious how to solve them because you'll have done it so many times. And this is where, when we're doing our algebra, I'm going to divide through now by 5m, and the m will cancel just by algebraic fractions. So we have got a is equal to g over 5, which is 1.96, therefore 2.0 meters second to the minus 2 to 2 significant figures. Comment on any modelling assumptions used. So we had smooth pulley, so the tension is the same throughout, and inextensible, the acceleration is the same throughout. That should say part B, not part C. Moving on, part C. Find the tension in the string. So what I want is the two formulas that I've just been working with. So if I use the formula for Q that I worked with before, and I had that acceleration was equal to g over 5, we got it at 2.0 to 2 significant figures, therefore I can work out this value for t. Now normally in an exam question it would say in terms of m, because in this case that value of m is not going anywhere, so that is going to stay with us. So the value of t in terms of m is 24m newtons to 2 significant figures. Part D. Find the force exerted on the pulley by the string. So I talked about this briefly at the start of this part. So the pulley, if you think about the forces that are acting on the pulley, particle P is pulling down and particle Q is pulling down, and by Newton's third law that force is equal and opposite to the original tension. Now when this system is sat at rest, if P is not moving anywhere, what you would end up with, if we just focus on P, so when it is at rest, so with no acceleration, what we end up with is T is equal to 2 mg. Just think about it. Here's the equation for F equals ma for that particle. If A is equal to 0, then T must equal 2 mg. So T would be equal to the weight, which makes sense. It's when we have acceleration that these forces vary slightly. So it's easy to think that the forces acting on the pulley are the two weights, but it's not. It's to do with the tension that's in the string, so just be careful of that. But if we look at the pulley as a system in its own right, so when we consider the pulley, the forces that we're considering are the two tensions. Okay, so when I'm looking at the force on the pulley, it's just equal to 2T. Now do be careful here. If I use the 24, which is the rounded value, I actually go slightly, I lose a little bit of accuracy. What we had up here with this value here was 23.52 m, and when we double that, what we actually get is 47 m. So that's using the exact value. So do be careful, you do need to be using original values. That's an example where your rounding is kind of on the border and it hasn't quite filtered through. If we then look at part E, find the distance moved. As soon as distance, you should now be thinking suvats. In the first 4 seconds, so that's given me the time, I want to find the distance. We started from rest, and we know that our acceleration is 9.8 divided by 5. It's the same suvat equation. So even though these are given to you in the exam, in the formula book, so you get all your suvats in the formula book, you should start recognising some of them because you use them a lot. And this is one that you do use a lot. And therefore when I put all that in, we get 15.68. which is equal to 16 newtons to 2 significant figures.